All right, thank you for the opportunity to speak, and thanks to the organizers for putting together such an exciting conference. So today I'll be telling you about Potts lattice gauge theory and how the Plaquette random cluster model that Paul mentioned to you yesterday is a cellular representation of it. I'm going to start with just a couple basic definitions, and then I'll get into some motivation and background for this work. Okay, so like in Paul's talk, I'll be talking about random subcomplexes and random cochains as well on the cubical complex ZD. So as you know, in lattice statistical mechanics, often your system is defined with respect to the nearest neighbors graph on the integer lattice. So the cubical complex is defined similarly, except you add in higher dimensional faces as well. That is, in addition to the 0 cells vertices and the 1 cells edges, you also have the 2-dimensional faces, which are unit squares whose corners are integer lattice points, and we'll be calling those plaquettes. In our papers, we also talk about higher dimensional plaquettes, but to keep things simple today, I'll mostly be talking about 2-dimensional plaquette percolation. So the simplest model we're interested in is that of Bernoulli plaquette percolation. So 2-dimensional Bernoulli plaquette percolation on Z3 is the random 2 complex that you obtain by starting with the vertices, all the vertices and all the edges, and adding the 2-dimensional plaquettes independently with probability P. The model of Bernoulli plaquette percolation was first introduced in this paper of Eisenman, Shays, Froelich, and Russo. I think it was in 1982 or 1983. On a sharp transition from area law to perimeter law in a system of random surfaces. Before I go on, let me say that this is really a seminal paper in the field of percolation, and many of the fundamental techniques in percolation theory today were first developed in this paper, I believe, such as block bond renormalization, sprinkling, slab percolation, and so on. But what was the main question of interest in this paper? In Bernoulli plaquette percolation, they studied the asymptotic probability that a rectangle is bounded by a surface of plaquettes as both dimensions of the rectangle are taken to diverge. As we'll see later, there is some subtlety in defining this, and in fact, for the definition we'll want to use will depend on the model we're considering. But for now, just take it to be your geometric intuition for this event. So their main theorem showed that there was a sharp phase transition for the asymptotic behavior of this random variable. To be specific, in the subcritical plaquette percolation regime, this is where your probability is less than 1 minus the critical probability of bond percolation on the integer lattice Z3. These arguments are done via a duality argument with bond percolation on Z3. In this subcritical regime, the probability your rectangle is bounded by a surface of plaquettes decays exponentially in the area of the rectangle. Whereas in the supercritical plaquette percolation regime, this is where your probability is greater than 1 minus the critical probability of bond percolation on Z3. You have perimeter law decay in this probability. So you notice you squint here, that's not exactly what's stated here. They have this pi c and rho c hat. These were different thresholds for bond percolation on Z3 that were conjectured at the time to equal the critical probability, and that was proven about 10 years later by Grimmett and Marstrand. So in my talk today, as an application of this cell complex representation, in my talk today, as one application, we will generalize this to a family of dependent plaquette percolation models. And in my paper with Paul, we also generalize it to higher dimensional Plaquette percolation in codimension 1, so d-1 dimensional Plaquette percolation on ZD. So for today, I'll be talking about concentrating on 2-dimensional percolation in 3 dimensions. Okay, so what is the motivation for looking at a dependent system of plaquettes? And that motivation is part of the same motivation for that 5-author paper. They wrote that their motivation came from an analogy with random variables in lattice gauge theory. And they wrote that for Ising lattice gauge theory, which I will define for you later, it's a spin model which assigns Z2 spins to the edges of a cell complex. They wrote that a phase transition for the random variable of interest, the Wilson loop variable, can be traced exactly to the geometric effect described there, which is the event W gamma for a system of interacting plaquettes. And while there is a reference there, it was in preparation, and the follow-up ended up being this, which is topological anomalies in the n-dependence of n-state Potts lattice gauge theory. So they ran into some issues that require some knowledge of topology to work out. So I will explain the anomalies that stymied this effort and show how to account for them. And that will lead to a cellular representation of Potts lattice gauge theory where a Wilson loop variable equals the probability that the loop is bounded by a surface of plaquettes when defined appropriately. Okay, so first I will tell you what Potts lattice gauge theory is. So I'm a topologist, so I'm going to use the language that I know, which is a little bit different than the language if you read some of the recent papers on Ising lattice gauge theory, for example, is I like to talk about our state space as cochains. So the cochain group on a cell complex X is just going to be an assignment of spins in an abelian group to the I-dimensional faces of that cell complex. If you're more used to the traditional terminology, you would call this like a discrete I form. But I'm going to stick with what I am used to. Okay, let's think about some examples of cochains that we know. For example, if we're looking at the Ising or Potts models, our state space is the assignment of spins to the vertices of a graph. That's the same as a 0 cochain. And there's also a 1 cochain associated with the classical Ising and Potts models, which is you can assign a spin to an oriented edge from V to W as the spin at W minus the spin at V. And notice that the spin you assign to the edge depends on the orientation of the edge, which is, why we would want to make sure that we're assigning spins to oriented faces rather than to just faces. Though if we are G equals Z2, it doesn't matter. Okay. And the key algebraic operation on cochange, which corresponds to, I guess, a discrete derivative operator, is going to be this co-boundary. So I already mentioned the co-boundary of a 0 cochain assigns to an oriented edge the difference in spins on the incident vertices. And then when we take that up a dimension, if we have a 1 cochain, so an assignment of spins to the edges, we can take the co-boundary, and that will take the oriented sum of the spins on the incident edges is assigned to the 2 plaquette. So for here, this is Z2 assignment to the edges here. We have 1, 1, 0, and 0. So then our co-boundary is going to be the sum of these spins, 1 plus 1 plus 0 plus 0 mod 2. So 0 is what the co-boundary of F assigns to this 2 plaquette. Okay. So with that notation, we can write the Hamiltonian for the Q-state Potts model in a way that makes it amenable to generalization. So recall that the Q-state Potts model, the energy is defined in terms of the number of edges for which the spins agree. So that's exactly the number of edges where the co-boundary vanishes. So we can define this Hamiltonian as negative the sum over the edges of the indicator function of the co-boundary operator vanishing. Yes?
In the previous slide, you wrote co-boundary in modulo 2 form. Now it will be modulo Q.
Yes.
So that was just an example for easing.
Yeah, that was just an example for easing. Yeah. So yeah, when you do ZQ, you need to worry about the orientation. That's the only real difference. So then your Hamiltonian, this is the Q-state Potts model, which you all know, can be written in this form. And once we write it in this form, we can just change our 0 to an I, or for today, I will just be changing it to a 1. And then we get the Hamiltonian for Potts lattice gauge theory. So that is, again, our state space is assignments of spins to the edges of our cell complex. And now our Hamiltonian is the sum over the two plaquettes of the indicator function of the co-boundary vanishing. So it's the number of non-frustrated plaquettes, you might say. So here is another picture for Z2 rather than ZQ. And you can count up and see that exactly the plaquettes shaded gray are the ones where the co-boundary vanishes. So our Hamiltonian gives us the value of -6. OK? And that allows us to find Q-state Potts lattice gauge theory as a random one cochain, which is given by this Gibbs measure. Now, in my talk, I will be stating some theorems for Potts lattice gauge theory on Z3, and also on ZD, on general cell complexes, some of which may be infinite. And this definition only works for finite cell complexes. But standard constructions with infinite volume limits work. You can see our paper for how to construct them from the cell complex end of things rather than from the spin end of things. But there's also standard references for the spin end of things for that. So just believe me when they exist and behave nicely. OK, so just a little history. So the Ising lattice gauge theory was actually introduced before lattice gauge theory under the name of a generalized Ising model by Wegner in 1971. And he introduced it for assigning spins to any dimensional cell in a cell complex. And then later, the Potts lattice gauge theory was introduced by physicist Kogut et al. In 1980, where they were viewing it as a relatively simple analog of lattice gauge theory. So just for your edification, I'm not talking about these today. Is that lattice gauge theory was introduced as a discretization of Euclidean Yang-Mills theory by the famous physicist Kenneth Wilson. And if you take your Z2 or Z3 and replace it by a complex matrix group, you model the fundamental forces of nature. Unfortunately, I will not be telling you about that today, but it turns out it's non-trivial even if you look at the simplest cases of Z2 and Z3, and actually we can prove some theorems about them and say some nice things. But I do want to say that in these more complicated models, the random variable of interest is still this thing called a Wilson loop variable, whose asymptotics on large rectangles is believed to be important to the physics that they describe. So what are these Wilson loop variables? I will just define it for Potts lattice gauge theory. If you know anything about the other lattice gauge theories, the definitions look a little bit more complicated. But for Potts lattice gauge theory, this is going to be a random variable so that if you have an assignment of spins to your edges, you basically take a loop gamma and you do the product of the spins around it. I generally use additive notation as an algebraic topologist, and sometimes we use the ring structure of ZQ. But for the purpose of this talk, you can just act like we're doing multiplication in the Q roots of unity. And you want your Wilson loop variable to be there so you can take expectations in the complex numbers. So it's, yeah, you assign Q roots of unity to your edges. You have a loop, you take the product of the spins, and you're wondering what is the expectation of this product. Okay, so the conjecture is for Potts lattice gauge theory on ZD that you get this thing called a deconfinement transition. This comes from the Wilson paper, why you call it that. But the conjecture, and this looks a lot like that theorem of Eisenman, Shays, Froelich, and Russo I showed you. So the conjecture is that if you take rectangles, or I guess it's a rectangular boundary, that should say we want to have a one-dimensional thing we evaluate our cochain on. So a rectangular boundary in ZD, then we should, in the high temperature regime, we should have area law decay in the expectation of the product of the spins around our loop, whereas in the low temperature regime, we should have perimeter law decay. So what is known about this? Yes?
Why is it important that it's a rectangle?
So we can handle, the proofs work for other nice loops. This just makes things a little nicer, as I don't need to add more hypotheses.
It doesn't have anything to do with the physics, does it? That it's a rectangle?
No.
It's just any large loop.
Any large loop where you don't want your perimeter to be growing faster than your area, right? So you want some regularity hypothesis. And yeah. Okay. But thanks for the question. All right, so what is known about this conjecture? So notice that actually I could come here and I could assign spins to I-dimensional cells, and we get a corresponding conjecture where area is replaced with volume, and perimeter is replaced by surface area. So what happens when we take I equals 0? Then I guess you could say your rectangle is a line segment in your lattice, right? The area of that rectangle is just the distance between the two boundary vertices. And the perimeter is a constant, too. So in this case, the conjecture is a theorem, which is the sharpness for the Potts model on ZD. Also, it's easy to show, multiple different ways of doing it, that, that the area law is the fastest you can decay, perimeter law is the slowest you can decay, and that there are perimeter law and area law regimes at sufficiently extreme temperatures. And there is some literature on Ising lattice gauge theory on Z3, which relates the coefficient in your area law decay of Wilson loop variables to something called the surface tension of the Ising model, which is defined in terms of mixed boundary conditions, the partition function for mixed boundary conditions for the Ising model. And then they used a spin flip trick and duality to show that that coefficient actually agrees with the area law decay coefficient of the Ising lattice gauge theory. So by, that was Brickmont, Leibowitz, and Pfister who showed that. So by this famous paper of Leibowitz and Pfister, showing that the surface tension of the Ising model does not vanish at criticality. You have that the dual regime corresponding to the supercritical Ising model in 3 dimensions exhibits an area law. So the other result from the literature is that of Linné, Messager, and Ruiz. I believe it's 1986. I'm missing the date here, who showed that when Q is sufficiently large, you have a sharp phase transition at the self-dual point in 4 dimensions. Now, it'd be really nice to do that in lower with an effective Q, but we don't have that technology yet. And so one of the theorems I'll be telling you today is we proved the analog of the ACCFR result for this Potts lattice gauge theory on Z3. So we show that it exhibits a sharp phase transition from area law to perimeter law for Wilson loop variables, dual to that of the Potts model in 3 dimensions. Okay, and our technique for doing that is to build a cellular representation of Potts lattice gauge theory. Any questions before I go on to that? Yes?
Your critical betas there are different, right?
Yes.
Actually, they're supposed to be the same.
Yeah, so I guess our result, except for q equals 2, where it's known that they are the same, our result is conditional on that conjecture. Yes? The conjecture that the slab threshold for the classical random cluster model equals the threshold for the random cluster model. Yeah?
And
Yes?
you also get the version of with codimension 1, you replace the cubed by ZD,
Yes.
but not the codimensions 2 and higher. So.
No, those will require something else. Yeah. Though our technique, our cellular representation works for any I and any D, which is what I will tell you about now. Okay, so first let's review the classical random cluster model, the graphical representation, or one of the graphical representations of the POTS model. So the random cluster model takes parameters p in 0, 1 and non-negative q, and it is, I guess, on a finite graph. It's a random subgraph whose probability is proportional to p to the number of edges, 1 minus p to the number of complementary edges, and then q to the number of connected components. So the key fact about this, or first key fact about this, is the Edwards-Sokal coupling, which is that the Q-state POTS model can be coupled with the random cluster model with same parameter of q. This is when q is an integer greater than or equal to 2. And p is 1 minus e to the negative beta, so that the conditional measure of our dependent bond percolation, random cluster model P, is just Bernoulli percolation on the edges where the co-boundary vanishes. And the conditional measure of our spins given our random cluster model is assigning independent spins to each component. So if you've gotten a little ahead of me on the cochains, I'm going to define cocycles for you later. This is just a uniform random cocycle. That's the same as the assigning independent spins to each component. And what makes this coupling especially useful is that you can relate your order parameter of interest, so your spin correlation function of the Q-state POTS model tells you how much does your probability that 2 spins on vertices differ from the probability that you roll a Q-sided die for each. And the connection correlation theorem tells you that your spin correlation function is just 1 over q times a topological quantity, which is the probability that the vertices are connected in the corresponding random cluster model. Okay, so we would like to generalize this. But before we do that, I will need to tell you a little bit about homology and cohomology, just very quickly. I hope you remember some stuff from Paul's talk yesterday, because he went into a little more detail. So again, you may recall these figures from Paul's talk also. So given a cubical complex X, your chain group Ci of Xg is just the group of formal linear combinations of your I-dimensional faces of X. And then we can define the boundary to be the signed sum of the incident faces. So here it's just the boundary of our 2 Plaquette sigma is E1 plus E2 plus E3 plus E4, because they are oriented appropriately. If we flipped the orientation, we get a negative sign. Okay? And then we can define a G-linear function. This defines a G-linear function just by extending it linearly. So here, the boundary of the sum of these 4 plaquettes is just what agrees with your geometric intuition. It's the outside of that. Okay, so very fast. Now that we've defined this G-linear operation, we can talk about the kernel of it. So that is the group of cycles. And then the image of the things that are boundaries are just called boundaries. All right, and actually we won't be using, well, I'll say my notation will use cohomology rather than homology, so you can just, or I guess I do use notation for homology, but all we'll need to know is that you're 0 in homology if you are a boundary. We'll use that to define the correct notion of this bounded by a surface of plaquettes. Okay, is this too fast here, or people okay? Okay. Anyway, so I'll just want to say a little bit more about cochains. Is you can also extend cochains, our assignment of spins to the I cells. You can extend that linearly and get a that's traditionally how it's defined as a G-linear function on the space of chains. And all that's going to matter for us about this today is if we have a one chain, which is going to be the boundary of a rectangle. It's actually going to be a one cycle. So all of these AIs are going to be 1 or -1. And all this is saying is we can evaluate our, actually I kind of used this already with the definition of the Wilson loop variable, but you can evaluate your F on gamma. This is the same as W gamma, right? This is in this case, an additive notation. It's the sum of spins around your cycle, or the product if you're thinking about it in terms of roots of unity. Okay, so all right, so we already defined the co-boundary map. So that is, you take an I cochain, you can spin that up into an I+1 cochain by evaluating it on the boundary of a chain. Okay? And as before, we have the group of cocycles. So that's going to be the kernel of our coboundary, and our group of coboundaries, which are the image of something I-1 cochain. So if you're more used to thinking about differential forms, this just cocycles correspond to closed differential forms and coboundaries to exact differential forms. So if you're more familiar with that, just say that in your mind when I say cocycle or coboundary. Okay. And then the cohomology group is just the quotient of closed mod exact I cochains. Good? All right. Finally, I can tell you about now with all that technology, I can tell you about the cell complex representation of Potts lattice gauge theory. Okay, so to just restate our goal is we'd like to couple Potts lattice gauge theory with a dependent two-dimensional plaquette percolation so that Wilson loop variable expectation is the probability that the loop is bounded by a surface of plaquettes. And we are not the first people to have tried to do this. In the 80s, there were a number of efforts by physicists to take the random cluster representation of the Potts model and make it work in higher dimensions. And these were stymied by the fact that they were not careful about the topology. And this was nicely outlined in that paper of Eisenman and Froelich I mentioned earlier of so-called topological anomalies. All right, so there are, I guess, 3 main topological anomalies they noticed. The first couple, or they're relatively minor, is you might think coming from your random cluster model in the plane, right, where you have number of components, that you can just say, okay, we can take a look at the number of independent loops or the number of independent closed surfaces. But it turns out that your number of components, it doesn't depend on your coefficient group for homology. It always equals the rank of your 0 homology. But the number of independent loops, which I'm defining as your rank of your 1 homology, and the number of independent closed surfaces do. And I'll have a picture where that is the case in a second. Okay. Or actually, it's a picture illustrating the other one, but it's Yeah, you can close it up. So the physicists were led astray by this because they weighted a random 2 complex by the number of independent closed surfaces, but they weren't careful about it. And I think they ended up using Z2 coefficients, which works for the Ising lattice gauge theory, but it doesn't work for any of the others. And then there was this other attempt I think they ended up, my interpretation is they ended up talking both about when G is Z and when G is Z2, but they ran into difficulties because of that. So the second, more minor topological anomaly is that when Q is not prime, you might not be able to write your probability in terms of Q to the rank of it, because this can have something called torsion. So instead, we're going to use our weighting factor as the number of elements in your I-1 cohomology of your 2-dimensional, so I guess 1-dimensional cohomology of your 2-dimensional cell complex. So that is the I random cluster model. Looks just like your 1 random cluster model, your classical random cluster model, so p to the number of plaquettes, 1 minus p to the number of complementary plaquettes, and then the size of your I-1, I guess here where we're doing it for 2, so it's the size of H1 of your cohomology with coefficients in ZQ. So the definition does simplify if Q is prime. If Q is prime, then ZQ is a field, and then you do have this equality up here holds. And that definition actually we found was discovered earlier by Hiraoka and Shirai in 2016. They were not interested in the connection with Potts lattice gauge theory. Rather, they were looking at this model on a complete cell complex, and they were looking at its relationship with a generalized Tooth polynomial. And then I guess Paul and I have 2 papers on this. And in our first paper in 2022, we ran with the field definition because we were interested in homological percolation, and that works out when we have a field, but there are some difficulties when we don't. So we worked out the details for the case when Q is prime there and suggested this definition. And then the details, making sure that this actually is the right definition, were worked out independently in our 2023 paper and also by this paper by Shklarov. OK, so here's our definition. So why does this help us? So you can prove that if Q is an integer greater than or equal to 2, P equals 1 minus e to the negative beta, that you can couple the Plaquette random cluster model with Potts lattice gauge theory in a way that exactly generalizes the classical coupling between the Potts model and the random cluster model. That is the conditional measure of your Plaquette percolation, given your assignment of spins to the edges, is just Bernoulli Plaquette percolation on the plaquettes where your spins sum up to 0 around the boundary. And then your conditional measure of your spins, given your Plaquette percolation, is just the uniform measure on this finite group of 1 cocycles on your Plaquette percolation. OK. And to make this useful, we want to relate it to a Wilson loop variable. So here, the third topological anomaly, as I'll say more on the next slide, is that the definition you want for being bounded of a surface of plaquettes, it depends on Q. So here I'm going to define V gamma of Q to be the event that we are a boundary in the homology with coefficients in ZQ. And actually, some of this subtlety was noticed in that first 5-author paper. And they explained in this figure that this is an example where our rectangle is bounded by a non-orientable surface of plaquettes. So this means that we are a boundary when coefficients are taken in Z2, but not when we are taken for Z3, for example. So there is that dependence. And also I wanted to point out in this figure is that in codimension 1, So for two-dimensional plaquette percolation on Z3, we have a nice dual characterization of it, which is that the event V gamma occurs precisely if there is no dual loop whose linking number is non-zero modulo Q. Okay, that's a mouthful, but you can just see in this picture that you have a loop, your dual loop shown here, that goes through the tube. This has linking number 2 with your rectangle. So that obstructs V gamma of Q for any Q other than 2, but not for Q equals 2. Okay? So with that correct definition of the Plaquette random cluster model and the event V gamma, we can state this generalization of the connection correlation theorem, which is that your expectation of your Wilson loop variable in Potts lattice gauge theory equals the probability that you are a boundary in the homology taken with coefficients in ZQ. And yes, this does work when we're in ZD. It works in any cell complex, and if you replace one with I as well. So we hope it will have many uses for that. And it's a little more complicated with this, but the third and perhaps main topological anomaly noticed by Eisenman and Froelich is that this fails if you take the wrong definition of V gamma. If you take it with coefficients in the integers, you get something that's provably not equal. So you needed the right topological definition to get the equality. OK, I'm going a little faster than I thought. Let's see. So what consequences? We have some pretty fast consequences from the definition of our cell complex representation and the generalization of the connection correlation theorem. So first of all, you can find new proofs of a lot of nice things about Potts lattice gauge theory. For example, that you get high and low temperature regimes where area law and perimeter law things hold. You can have new proofs of certain correlation inequalities. Those follow pretty much immediately. The coupling allows us to generalize cluster algorithms for the Potts model to Potts lattice gauge theory, including the Swenson-Wang algorithm, as you saw on Anthony's poster yesterday. Also, the coupling allows us to interpret the result that Paul told you about yesterday in terms of homological percolation. So in particular, you can look at two-dimensional plaquette percolation on the 4 torus, and you get a sharp phase transition. You can view that as saying that you have, if you look at the Swenson-Wang algorithm, the Plaquette-Swenson-Wang algorithm for the corresponding one-dimensional Potts lattice gauge theory, you get a phase transition when it starts to have global moves, right? When you start to have updates that are large relative to your torus. Okay? And then last but not least is we have this generalization. Oh, that got a little cut off there. This generalization of the direct generalization of the result of Eisenman, Shays, Froelich, and Russo, which says that that you have area law and perimeter law regimes for your two-dimensional plaquette percolation on Z3 that are dual to corresponding regimes for the random cluster model on Z3. So in particular, if your random cluster model on Z3 is subcritical, this P star will, this is a decreasing function, so this changes the order. It takes the subcritical regime to the supercritical regime, that if your dual random cluster model is subcritical, then your plaquette random cluster model is supercritical, and you have perimeter law decay. And on the other hand, again, this is conditional on a slab, a conjecture on the regularity of the random cluster model in slabs, that if your random cluster model is supercritical in a slab, this implies that you have area law decay in your probability that your loop is bounded by a surface of plaquettes when defined appropriately. Or actually, these results, they work for any definition of the V-gammas. You get the transition at the same point. Yeah. So let me point out that these constants are well-defined and independent of your family of rectangular boundaries. Let's see, what else? And one of them, I think it's the perimeter law one. It has a wider range of independence from boundary conditions. Yeah. OK. Oh, and also there's the hypothesis of suitable. That's only to make sure that this constant doesn't depend on your choice of rectangles you get. You can prove a perimeter law pretty easily without this. But to get your sharp constant, you need to have that one of the dimensions isn't growing like logarithmically slower than the other for our proof to work. And finally, let me note that with the our connection correlation theorem, that this implies the corresponding result for one-dimensional Potts lattice gauge theory on Z3. That's, I guess, not quite finishing the program started by ACCFR, because we'd like to do this for other dimensions as well, but showing that there is this exact relationship between the Wilson loop behavior in Potts lattice gauge theory and this geometric effect. OK, so I have 9 more minutes, so I can say a few, or maybe let's see if there's questions first. I've been going a little fast, and I can say a few words about the proof.
Any conjectures about when P equals the critical value?
Oh, when P equals the critical value. So note when Q equals 2, it's known that it follows an area law, right? So I guess this is, so our proof of the area law, it follows the same proof idea, though we need to use the random cluster representation to make it work, as in Brickmont, Leibowitz, and Pfister. So it's if you can show that what is the conjecture on surface tension at criticality for the Potts model in 3 dimensions? It's the same as that.
Yeah, so it's probably about whether it's a first order or second order phase transition for the ordinary pods, maybe in that dimension.
Yes.
So dimension 3, maybe 3 is the critical value for this.
Yeah. Any other questions? Yes?
So I assume this Plaquette random cluster model has FKG.
Yes.
And you have a result stating that for low temperature you get one behavior, for high you get the other. The obstruction to proving the existence of a critical point is just is it just excluding that something else other than area or perimeter law could happen?
Yes.
Or, okay.
But who knows what happens at criticality, right? Yeah. Yeah. I mean, if you could show that, you'd be done. Yeah. All right. So I'll say a few words about. Oh, there's some references. I wasn't thinking I'd get to the point where I say. So the proof of this deconfinement transition is once we have the Plaquette random cluster model and the correct definition of V gamma in hand, and a little bit more about the duality properties, it isn't that difficult, and we can modify existing techniques to make it work. In fact, the perimeter law argument is nearly identical to that of the original one, though showing that there is a well-defined constant for any averaging family, that gets a bit more difficult because of boundary conditions. Though if you want to know the details of that, that's in the paper. And then the area law argument is similar to that of Brickmont, Leibowitz, and Pfister, though we work with the Plaquette random cluster model instead because you can't do the same spin flip trick that worked for the Ising model on Z3. OK. And so we need, so first of all, the trivial bounds. If we have a rectangular boundary, then V gamma occurs if all the plaquettes in the rectangular occupied, so that gives us a trivial area law lower bound. And our trivial perimeter law upper bound is given by removing all the plaquettes adjacent to gamma. That obstructs the event V gamma. Okay? And then proof ingredient 1 is that, so I did sweep boundary conditions under the rug, but I guess you kind of need them here, is that if you take the dual of the random cluster model on I-dimensional random cluster model on ZD with free boundary conditions, that is dual to the wired random cluster model on ZD. And the duality works, I guess, as shown in this picture and is explained in Paul's talk, that, for every square plaquette, there is a unique edge going through the center. So you can take doing the two-dimensional plaquette random cluster model, your dual is going to be a bond percolation. And then using Alexander duality and the Euler-Poincare formula, so some facts from algebraic topology, you can show that they are in fact dual. That's what first led me to this model, was I was working on homological percolation with Paul, and I noticed that, wait, to get this to work, we can just use Alexander duality and the Euler-Poincare formula to prove homological percolation for this other model. So that led me to this, that led us to this whole line of research, is realizing this duality here. Okay, and then the second proof ingredient is we convert our problem into something of one-dimensional bond percolation, which is relatively easy to work with. And it says that if we're in codimension 1, then our V gamma of Q occurs precisely if there is not a dual loop that has a non-zero linking number modulo Q. So the proof of this, again, is Alexander duality. Okay. Maybe I should call it here because I don't think I can get through the proof sketch in 3 minutes. So I just have some nice pictures of some of the arguments. But here are some of the relevant references. And thank you for your attention, and I look forward to answering any questions.